Good day and thank you for joining me in this video lecture where we will dive into the fascinating world of the moment distribution method. In today's lecture we will solve a frame indeterminate frame to find the internal response of the frame. So here the detailing of the frame is given 5 kip per feet is the load intensity for BC span. 20 kip load is applied at point B horizontally. In question it mentions that at point E and D there is a fin support, at point A there is a fixed support. So we will find the internal response by moment distribution method. Since frame is the combination of columns and beam, there are two types of frame. One is no sidesway frame and another is sideways frame. This is the example of no sidesway frame in which horizontal deflection is not permitted, which is restrained. Horizontal deflection is restrained. So in moment distribution method, the first and the most important step is to calculate the stiffnesses for each span, each member from each side. So we will calculate the stiffness for AB, BC, CD and CE. So first we will calculate the stiffness KAB. KAB will be equal to KBA. So in actually we know that at fixed support the stiffness will be infinity, but we still by using formula we will find the stiffness for AB also. Remember this is the most important point of this video lecture. So the stiffness of AB, since at point A there is a fixed support, so we still find the stiffness of AB. So KAB will be equal to KBA, since this is a single frame having the same length. So we will use the flexure stiffness formula. Flexure stiffness formula is 4EI by L. E is the elastic modulus, I is the moment of inertia, and L is the length of AB span. For KAB, remember this, KAB will be equal to KBA. Remember this. So by putting the value of L is 15, we will get 4EI by 15. Now we will calculate the stiffness for BC, which is also equal to the stiffness of CB. Remember this, from each side the stiffness will be equal because the span length is same. So by using the same flexure stiffness formula for EI by L, instead of L we will put this span length 18. Now we will calculate the stiffness for CD and CE. Remember this, at point C we will use the modified stiffness formula. At point E and D there is a fin support. When the far end is fin or ruler, so the stiffness formula will be 3EI by L. Remember this is the modified stiffness formula when the far end is roller or pin or hinge support. So the stiffness formula will be 3EI by L. L is the length of that span. So for KCD, instead of L we will put 15 feet. For KCD we will put the length is 12 feet. For KCE, for KCD we will put the respective span length, which is 15. So remember this. For when the far end is a hinge or roller, we will find the stiffness for one end. Remember this. So in this we calculate the stiffness for each span length. With the help of stiffnesses we will find the distribution factor, which is the second most important step for the moment distribution method. So we will calculate the distribution factor for AB, BA, BC, CB, CD and CE. So for distribution factor we will use simply the basic formula for distribution factor, which is the stiffness of member divided by total stiffness at joint, so attached joint. So we will add, so by dividing we will get the distribution factor. Distribution factor told us that by what percent it takes a moment, distribution moment. So for AB, distribution factor for AB will be 0 because there is a fixed support. Remember this. Distribution factor for hinge or roller is 1, for fixed is 0. So now we will calculate distribution factor for BA. From B side, what will be the distribution factor? Distribution factor for BA is equal to stiffness of BA. Stiffness of BA divided by total stiffness at A, means KBA plus summation means total stiffness for B, KBA KBC. So by putting the values, we will get the distribution factor for B8. Remember this. Now we will calculate the distribution factor for BC. Now we will calculate the distribution for factor for BC. So DF BC will be equal to KBC divided by KBC means stiffness for BC plus KBA. Since there are two members attached at joint A, so we will add two member stiffnesses in denominator. So we will get the distribution factor for BC, and for distribution factor CB will for CB. Remember this, at joint C there are three members are attached. One is CB, CE and CD. In denominator we will add three member stiffnesses. Distribution factor for CB will be equal to KCB means stiffness of that member divided by total stiffness at joint C. So one is KCB, another is KCD, and the last is KCE. We will put all the values in respective terms. We will get the distribution factor for CB. Now we know that for hinge roller support the distribution factor will be equal to 1. Distribution factor for CE and DC will be equal to 1. So in second step we calculate the distribution factor for each span with the help of stiffnesses. So these are the stiffnesses for distribution factor for AB. BC is 0.545, 0.330 for distribution factor for CB, and for CD is 0.298, and for CE is 0.373. and this is the second method how we will calculate the stiffness. So you can also use the basic formula for distribution factor for each member. So distribution factor for CD and DC and EC will be equal to 1 because there is a hinge or pin support at point C. Now the third step is to calculate the fixed end moment. Remember, this is the third step for the moment distribution method. So by definition of moment distribution method, applying locking and unlocking phenomena for each member. So take this member AB, HAB. So I want to make this member horizontally. The fixed end moment for this is the joint A, joint B, and the fixed end moment for this is a fixed end moment AB, and the other side fixed end moment is BA. In this the no vertical load is applied, so the fixed end moment for AB and BA will be equal to 0. Remember this, there is no external force for AB span on AB span, so the fixed end moment for AB and BA will be equal to 0. Now we will calculate the fixed end moment for BC span. I want to make only this span, so this is the B joint, and C joint. The uniformly distributed load will be applied UDL of intensity 5 kg per feet. The span length is 18. So fixed end moment from this side will be equal to fixed end moment BC, and fixed end moment from this side will be fixed end moment CB. So by using the formulas which are mentioned in books, so which is for fixed end moment BC, it is the anti-clockwise moment. We will take anti-clockwise negative. So fixed end moment for BC will be equal to fixed end moment for BC will be equal to minus WL square divided by 12. L is 18 and W is the intensity, which is 5. So by putting the values we will get the fixed end moment from B side, BC span. Now we will calculate the fixed end moment from CB span, which is clockwise. We will take positive, and the same by using same formula WL square divided by 12 we will get the fixed end moment from CB side. Now we will calculate the fixed end moment for CD span and CE span. So there is no external force, so for both fixed end moment will be equal to 0. So this is the third and most important step for the moment distribution method. So we only calculate the fixed moment from BC for CB, which is minus 135 kb per feet, and for CB it is 135 kb per feet. For other members AB, BA, CE, CD, which is equal to 0, remember this. For other sides, other member, the fixed moment will be equal to 0 because there was no external force. Now the fourth step is to make a table. The table is consist of rows and columns. The first row is joints, the second row is member, the third row is distribution factor, fourth row is fixed moment. Make a separate rows, remember this. And the fifth row is distribution moment, sixth row is carryover moment, and seventh is distribution method. Now repeat this carryover distribution in your easiness. Make this carryover and distribution moment in separate row. Remember this for your understanding. Make separate rows. So you will calculate the moments at joints in each joint. So the first row is joint. So there are for the given frame there are 5 joints, A, B, C, D and E. In the second row mention that how many members are attached to the respective joint. At A there is only one member is attached, AB. At B there are 2 members attached, one is BA and another is BC. At joint C there are 3 members are attached, one is CB, CD and CE. And at joint D only one member is attached, DC. At joint E only one member is attached, which is EC. So the third row we mentioned distribution factor. We calculate the distribution factor with the help of stiffnesses, which is for A it's 0, for BA span is 0.545, for BC is 0.455, for CB is 0.330, for CD 0.298, for CE 0.372, for D and E is 11 because there was a roller or hinge support. There was a hinge or hinge support at point D and E. Now the fourth row is fixed end moment. We calculate the fixed end moment for each member. The fixed end moment for A is 0, for AB is 0, for BA is also 0, for BC is minus 135, for CB is plus 135. And for the rest of the span CD, CE, DC and EC, the fixed end moment was 0. Now we will distribute this moment for each member. Remember this. We will distribute the fixed end moment to the each members attaching members. So the only fixed end moment are present at BC and CB span. So at joint E, at joint B, the only moment is minus 135. So we will take the net moment at joint B. So the net will be this fixed end moment plus this fixed end moment. So 0 plus minus 135 will be equal to the minus 135. So take the opposite sign of this net moment, which is the net moment is minus 135. So take the opposite value, which is plus 135. So multiply this 1 plus 135 to the distribution factor of this. We will get the distribution moment. So 135 multiplied by 0.545, we will get the distribution moment 73.6. Now the same plus 135 multiply this one plus 135 to the this distribution factor. This distribution factor we will get the moments 61.4. Remember, this is the first step from fixed end moment we will distribute this fixed end moment. So for member joint C, the only fixed end moment is plus 135. So we will find the net of this 135, add all the fixed end moment at joint C. so there is a 0 0, so 135 plus 0 plus 0, we will get 135 net moment. So take the opposite value of this net moment, we will get minus 135. So multiply 1 minus 135 to the distribution factor of this, we will get the value is minus 44.6 minus 40.2 minus 50.2. this is the distribution moment. At this joint there is no need to calculate, because we know that at last at the end we will get the zero moment. So when the joint is roller or hinge or pin support, so there is no necessary no need to calculate the distribute and carry over the moment at these joints. Remember this, because we know that at the end we will get the zero moment. So there is no need to calculate, take it, carry over the moment, distribute the moment, carry over the moment, and distribute moment at hinge or pin joint. Remember this. So we will not do this calculation, because we know that at the end there the moment will be zero. So this is the second fix. We calculate the fixed end moment and distribute this fixed end moment. Now we will carry over this distribution moment. Now we will see the distribution moment. Remember this. The distribution moment is 73.6, 61.4 minus 44.6 minus 40.2 and minus 50.2. so we will carry over this moment. So from each joint the moment will be transferred by half of the moment will transfer to the another member, another support. So we will carry over this moment. So since we know that the carryover factor is half, so we will distribute this half moment to the joint B. So half of the moment will transfer to the joint A. So 73.2 multiplied by 1 by 2, so we will get 36.8. this is the carryover moment. Remember this. Here is the distribution moment is 0, so take the half of 0, we will also get the 0. We will distribute this moment at joint B. Now at this joint at BC, some of the moment will transfer at CB. So from C, some of the moment will transfer at BC. So 61.4 divided by half, multiplied by 1 by 2, we will get 30.7. half of the moment will transfer from BC to CB. Now half of the moment will transfer from CB to BC. Remember this. At CB the moment is minus 44.6. half of this moment will transfer at BC. So half of this minus 44.6 is minus 22.3. So remember this. Also we know that at CD the sum of the moment will transfer to the DE and BC. So we will not do this calculation because both spin are hinge, so there is no need to calculate. So we only consider these joints. Remember this. This is your approach, that what you are doing. If you do this step, the calculation will be complicated, but in actual we know that at joint D and E the fix and the moments will be equal to 0, so we will not deal to this calculation. So there is no need of this calculation. So now we will distribute this carryover moment. So we will calculate this carryover moment. Now we will distribute this carryover moment. Take the opposite of this value is minus 36.8 multiply with distribution factor. We will calculate the distribution moment, which is 0. Multiply minus 36.8 with this distribution factor, which is 0. Now we will at joint B only the moment is minus 22.3. so take the opposite of this value is plus 22.3. so multiply this 22.3 with this distribution factor and this distribution factor, we will get the distribution moment plus 12.2 and plus 10.1. and also for this from B also for the moment present at joint C is 30.7. so take the net of this, which is also 30.7, and take the opposite value, which is minus 30.7, and multiply this net with this distribution factor, this distribution factor, this distribution factor. We will get the distribution moment for CB, CD and CE, which is this. So now we will carry over this distribution factor. So we will do this procedure until we will get the moments is 0.1, 0.1, or in the form 0.5, 0.4, 0.6, 0.7. So the limit is up to 0.5, 0.4, 0.6. so we will get these moments. Now at and at the end we will add this moment, this moment, this moment, this moment, this moment, this moment for each joint, for each member. So by adding these moments we will get 44.5. At joint A the moment is 44.5, which is clockwise. At joint BA is 89.2. At joint BC, at member BC, minus 89.2. Since the couple there is a couple at joint B, so it will be equal in magnitude but opposite in direction. One is clockwise and another is anti-clockwise. Now for CB, add these moments only: fixed moment, distribution moment, carryover moment. So add these all. So we will get the plus 115, which is the moment at positive moment at member CB. Now for CD, add these moments, we will get minus 51.2, so which is anti-clockwise moment. And for CE, add these, we will get minus 64.1. we will get this moment, which is anti-clockwise. So for CD, which is 0, we know that at pin the moment will be 0. At E the moment will be equal to 0. So we calculate these moments at A couple, at B couple and C. So now by drawing the SFD and BMD, for this we will use equilibrium equation. By equilibrium equation we will find the horizontal and vertical reactions. Remember this. For first we will calculate the horizontal reactions by taking each member. For AB we will take this, and BC, CD and CE. First we use the unlocking phenomena to calculate the internal response. Then by finding the internal response, horizontal and vertical reactions, we will draw the SFD and BMD for the given frame. For each member you can also draw the SFD and BMD separately. So this is the whole procedure for the moment distribution method of the given frame. The SFD, the moment diagram of the AB span will be this. For BC span is this. For CE is this. For CD is this. This is the only moment diagram. You will draw the shear force diagram and bending moment diagram by calculating the reactions. By taking each joint, then calculating the reactions, internal response, then drawing the SFD and BMD. So this is the last. We draw the bending moment diagram for the given frame. So this is the no sideway example. So thanks for getting the knowledge, and take care of yourself. Allah Hafiz.